me start over. Hello. Hope you're all doing well. From what I have seen, what I've already looked at for all the test scores I've gotten in, things are going very well there. I'm not especially worried about anyone's grades at the moment. So congratulations. The test grades will be getting out this week as I grade them. The way that it works is I will respond to the same email where you sent me the scores, where you sent me your answers with the score and a summary as to what you did on each question. Those will be going out this week. So speaking of this week, let's look at the calendar for the coming 2 weeks. I still have to teach though. So, let me start over again. Hope you're all doing well. You all have good weekends. And we're nearing the end of the semester, so let's finish strong and get on Thanksgiving, Christmas, and New Year's. It's going to be fun. So, last weekend, the weekend that just ended, was the test. During the rest of this week, you'll be starting to get your test scores back via email. And what we're going to be covering in lecture this week are additional topics. We're going to be talking about electricity and waves, maybe just spending about a day on each topic, one lecture on each topic, just to sort of hit on the main important things that I feel are important to know about them to successfully exist on this planet where electricity powers everything and where everything you've ever seen or heard happened because of waves. So that's what this week is. We're just going to hit sort of the big keynotes and hopefully the fun parts of all of those topics. And after this week, the week following, so that's the 16th through the 20th, is the last week of classes. So that will be pretty much entirely dedicated to wrapping up the semester and exam prep. We will spend a couple of these days going over the test we just took. I'll be even looking back at the first test, talking about what exactly is going to be on the exam, going over exam practice questions, entirely focused to making sure everyone is as prepared as possible. And the exams themselves, there will not be any assignments this week at all. There will be a homework set and quiz for the topics we covered this week. That will probably be due on this day, but that's the only thing resembling assignment that will exist that week. It's the last week of class and you guys need to rest and study. So, we do have a lab this week. We don't have a lab this week. Okay? No lab this week. Sorry, the week I'm pointing to. No lab next week. There is a lab this week, no lab next week, and then we have our exam days. I'm going to show you the exam schedule, because if you haven't looked at it yet, there's probably a few things you need to make note of. The school is having some exams on Sunday, so pull the calendar back up. Our exams are going to be the last full week of November. Thanksgiving is this day. And our exams, the school is having exams 22nd through the 25th. This class is officially scheduled to take its exam at 6:30 p.m. on Sunday. And the reason for this weird schedule is so that we can get everything done before Thanksgiving, so we can send you guys home and then you can stay there until after January, hopefully. Now, I know a lot of you probably aren't very enthusiastic about being here Sunday evening, taking an exam. The way that the actual exam taking is going to work, the document itself will be very similar to the way that tests look in terms of how the questions are ordered and read and the way the points are going to work, there'll be more points than I grade out of, so you can get some bonus points. It'll be about twice as long as a normal test, because there's about twice as much material on it. And mechanically, during this time slot, I will be in this room giving the exam physically to those who attend. But I will also be having my computer open with Google Meet active, such that people who cannot be here in person I'll basically be proctoring the exam to you over Google Meet at the same time.
So you have to join the exam?
Yes. So this class is scheduled to take its exams at 2 specific times. Well, okay. This lecture is scheduled for this time. I also have a different exam period for the other lecture of this class for Tuesday, November 24th at 11:30 a.m. And since it's the same class, just different lecture times, it's the same exam. And I don't care which one you come to or log into. So if for some reason, okay, I completely understand why this day might not appeal to you. So you have the option to come to this one. Just be aware that a bunch of other people are probably going to try the same thing. But on the other hand, I might have some people move into this one because they just want it over with so they can get out of here quicker. So I'm hoping it'll even out. But I'm trying to help you guys in that way. So again, I will be in here in the physical space administering a physical exam to those who are able to be here and would prefer to be able to tactile touch the document and work through it with me in the room to ask me questions. On all assignment, out of every assignment, it's the most important to ask your questions during the exam, since it's the single largest portion of your grade for one thing. And those who can't be here, at the same time as the in-person one, I'll proctor you over Meet. And I'm trying my best to hybridize what we've been doing with the school's usual exam policy, just because of the terms and practices and procedures I have to stick to. And after this period of days, exams are done, cut off. After this period on Wednesday, y'all can go about your holiday, and final grades will be due in. You'll be able to see all your final grades by no later than December 2nd. That's the day the grades have to be in by. And officially, since this class does not have any Wednesday exams, that means you've only got 2 weeks left maximum. You guys have survived physics, you're almost there. That's a lot of information already to start with, and I already need a drink of water. You guys have any questions about anything like this course for the rest of the semester?
How long will we have on the exam?
The official time slots are 3 hours. I'll probably be here a little longer than that, just in case. Unofficially. And if any student has academic accommodations for like extra time or a specific testing environment, those will be available. But yeah, I think officially all of these slots are supposed to be 3 hours long. Yeah, so that if for some reason you were taking an A exam and it took you the full 3 hours, you'd still have 30 minutes to get to your H exam if you had one. But I'll still be in this room. I'm used to giving you 5 hours on the internet tests. I'll be in this room for you as much time as long as you're not here till midnight. We all need this. Anything else? Okay. So, mistake. Okay. Everything that I just said, I will also write in an email and send out so that you guys have it written and don't have to worry about remembering it from your brains. Because I know I always forget half of what I'm told unless it's written down. Now, I'm going to show you the bright space page. We just did the test 2. The next 2 tabs beneath that, we have Chapter 9, Waves, and Chapter 10, Electricity and Magnetism. It says chapter just because they are separated topics, but it's really just going to be a one-day lesson on each of these things, just the highlights. And even though it's listed as waves first and then electricity, I'm actually going to start with electricity. They're in this order because of all of the notation and all of the documents for the way that this class is normally given, but because we're doing an electricity lab this week, I'm starting with electricity. So, in that tab, you click on this itself, you click on the tab itself, like the video lecture, the notes are right below it, are available to you. Because we're covering both of these short categories in 1 week, there will be one conjoined homework assignment for both of these things that is already uploaded. One conjoined homework assignment for both of these that is due next Tuesday. There is a lab this week. There is not a lab next week.
Is there a lab option for online?
Yes. Yes, there is.
Is the homework assignment on Sapling or is it on Physics?
It is on Sapling. I admit it probably wasn't there an hour ago. So, let us now begin looking at electricity. On the actual save file on my computer. So, any questions before we begin this supplementary topic? Okay. So, as I've been saying, electricity is rather important given the fact that most machines on Earth run on it. So, fundamentally, what is electricity itself? If you were to see a bolt of lightning, what physically is that? Okay, it's a very good guess, and you're not entirely, that is partially correct. There is a lot of energy involved in electricity, but the electricity itself is not pure energy. Because again, if you recall from many chapters ago when we first discussed energy, you cannot see energy. Energy is just a thing that matter possesses. Matter that has energy can do stuff, but you only see what the matter does. You don't see the energy itself, no matter what sci-fi or Dragon Ball Z might have taught you. So, in order for us to be able to see electricity, there has to be something physical going on. And yes, there is definitely energy involved, since we get energy through electricity. But that energy is being transferred through some physical happening. There's something physical going on as the energy moves. So you are right, but there's another piece to it. Now, what is physically happening is electricity is, at its simplest, a bunch of electrons moving from point A to point B. Electrons are one of the three fundamental particles that make up the physical universe around us. All physical matter, every atom, is made up of some combination of these three subatomic particles. Flashing back to, say, physical science or chemistry classes, I'm hoping that this diagram looks vaguely familiar to most of you. All right, what have I drawn? Very poor drawing of an atom, yes. And every single piece of matter is made up of atoms, and every single atom is made up of these things. So what part of the atom is this? Big blobby bit in the middle. Say it again. There are definitely protons in there. You are correct. So this is the place where protons do reside inside of an atom. Say it again. The nucleus. The core of the atom is called the nucleus. And the nucleus is made up of protons and neutrons. So I guess the body of an atom, I guess the actual matter part, is protons and neutrons. They live bound together, stuck inside of the nucleus of an atom. Now, I guess you could say this is sort of what most matter itself is, and electricity is not this. This makes up the bulk of your body right now. This is like the solid, the liquid, and the gas. Now, separate from the nucleus are these extra particles that spin around and orbit it, kind of like the moon orbits the Earth. These are the electrons, and we call electricity because it's made of electrons. Or it's also entirely possible that we call electrons electrons because they make up electricity. That's probably the better order for how the words were developed. These boys are not physically attached to the nucleus. They orbit the nucleus. That means they can leave the atom. These are stuck. These are not. They can leave. And they very frequently do leave. They will jump between atoms, and under the right circumstances, a bunch of electrons can go from one part of the object to another and surge as electric current. So the electricity itself is just a bunch of these things moving between atoms. So when you see lightning, what you're seeing is light given off by air that has a bunch of electrons traveling through it, which is exactly the same thing that's happening in those light bulbs. There's gas inside of the bulbs. Electricity, which is electrons, flows through the particles of the gas. They leave behind energy that makes the gas heat up and give off light. So what you see when you look at lightning is light given off by matter. That matter gave off the light because it was energized by electrons surging through it from point A to point B. So you could say that electricity is made of electrons. Electricity is moving electrons from point A to point B. And we only see this in electrons because they are the only particle that is not bound in the nucleus. Protons and neutrons can't move, so you can't make electricity out of protons. Now, all of these particles, they are made of matter, which means they have some amount of mass. Which makes sense. These are the things that make up matter. Every cell in your body is made up of these things. If you're cells have matter and they're made of these are made of matter, therefore they have mass. Granted, those masses are incredibly tiny. Protons and neutrons have a mass of 1.67 times 10 to the negative 27th kilogram, one of the smallest units of mass that exists. We usually think of neutrons as being slightly bigger than protons, which is not reflected in these numbers, but that's because it's not big enough to really matter most of the time. But the point is, they are very small. And electrons are even smaller. Electrons are the physically smallest fundamental particle. Their mass is easily like 1,000 times smaller. They're very tiny. They are actually the smallest form of matter that you're likely to ever interact with. And since they are matter, and since they have mass, that means that lightning has mass. Lightning is an object that has mass. That means lightning has weight. I don't recommend it, but you could hypothetically weigh a lightning bolt and get an actual number. Again, not recommended, but it's a thing that could be done. Now, all these particles have mass, but they also have something called charge. You've probably interacted with charge before, likely because you were rubbing like your hands together, or maybe your feet along with little socks across the carpet, or curled up in a warm blanket, and there was some sort of a static buildup, some sort of a charge buildup. All matter has some amount of mass and some amount of charge. Charge is similar to matter in that it's just a thing the matter possesses. Matter is defined as having some amount of mass and some amount of charge. Mass dictates an object's movement, inertial and gravitational properties, whereas charge dictates an object's electrical properties. And what's unique about charge is you can either have a positive charge, a zero charge, or a negative charge. You can only have positive mass. If something has mass, it's a positive number. But the three different particles have either a positive for protons, neutral for neutrons, or negative for electrons charge. Charge is measured in units of coulombs. That word will be spelled on the board momentarily. Coulombs is just the measurement of a charge. Notice that positive or negative, these are very tiny numbers. So if you can feel a static charge, it's because you have built up a lot of electrons. In order to build up charge, you have to physically pull in electrons and hold them in place so that there is a net charge in that area. Normally my body is neutrally charged. Normally I have as many protons as I have electrons, and they'll cancel out. If one proton next to an electron, the net charge is zero. See how they have the same charge but in opposite directions. So if this atom has the same number of protons and electrons, its charge will be neutral. But the way that I've drawn it, it has one more proton than it has electrons, which means it's going to have a net positive charge. If it had more electrons, it have a net negative charge. Whenever you have felt your hair stand up because of charge, or whenever you've been shocked by something, it's been because something has built up a charge by having a different number of protons and electrons inside of itself. The easiest thing to do is to build up electrons, since they move. You pull electrons away from something. And if you build up a negative charge, it's because you've rubbed against your wool socks and you've taken electrons away from that object, and now they're stored in your body. And those charges, once they build up, start to interact with one another. Is anyone here unfamiliar with the statement that like charges attract and opposite charges repel. Works the same way with magnets. Does that not sound familiar to anyone? Okay. This is the reason why. Charges, all charges will have some amount of force between them. And this formula here represents that force that causes like charges to repel from one another, like the north ends of a magnet repelling from one another. And it also explains why opposite charges are going to pull together, like opposite ends of a magnet. So, this formula is referred to as a Coulomb's law. The unit of charge from a second ago, measure charge in units of coulombs. It's the same word here. So this is how you spell Coulomb. This formula is called Coulomb's law, named after, I believe, his full name was Augustin Coulomb, Augustin de Coulomb, French. And this formula allows us to calculate what the force between two charged objects would be. So if you have two objects with charge, these two objects could be two charged wool socks. These objects could be your hair and when you were kids, you ever play on like a plastic playground equipment and went inside one of the like tubes you would crawl through and someone's hair stand up being attracted to the plastic of the tube?
Yeah.
That's the same kind of situation. Plastic would build up a charge because there's a bunch of kids moving through it. Charge will build up through friction. The tube has a net negative charge. It's going to interact with the negative charges in your body, and that's why you would see someone's hair drift towards it. This is the force that causes that drifting to happen. So the objects here can be anything. It could be hair versus playground equipment. It could be sock versus sock, hair versus balloon. It could even be electron versus electron. You can go that small. And it tells us that the force between any two charged objects will be equal to K, and this K is Coulomb's constant. This K is a constant. It is always the same number, which you will always have on your formula sheet. It is equal to 8.99 times 10 to the 9th power. It's a known constant for you. It's a freebie. The electric force between two objects is equal to K times both charges multiplied together. Within this formula, these lowercase q's represent the charge of the objects in question. Whatever two objects you are comparing here, you multiply both of their charges together. And then you divide all of that by the radius between the charges squared. So, if the two objects in question have more charge, the force between them will be bigger. Conversely, if those two objects are farther apart, the force between them will be weaker. Which is why when you say if your hair is being attracted to a balloon, you pull the balloon away and your hair sinks back down. Because the farther it is away from the balloon, the weaker the force is. This formula, the way that it looks, the way that it is arranged and formatted, and the things that are present in it, does it seem at all familiar to you guys? Yes, which I conveniently have written over here. This formula is basically the same in terms of formatting and the elements that are present and how they are treated to the universal law of gravitation. And the reason for that is because they are basically the same thing. Gravity and the electric forces are two different sides of the interactions between matter. Matter, the subatomic particles that we talked about, possesses mass, and those masses interact with each other through gravity. but they also contain charge, and those charges interact together through the electric force. They work the same way because they're almost the same thing. Each object gives off a field, and when it interacts with another field of the same type, we get a force between them. Gravitational fields interact to create gravity, electric fields interact to create electricity. And they both are just tied to some fundamental measurement of the particles in question, either its mass or its charge. And they're so similar because they are basically, it's weird to say that forces have siblings, but in this case, they really are siblings. There's 4 fundamental forces that hold every single particle in the universe together. And those 4 forces are gravity, electricity and magnetism, weak nuclear force, and strong nuclear force. These forces are all highly interrelated and highly interconnected, and they are literally holding the entire universe together. And because they're all cousins, different sides of the same weird 4-sided coin, they work incredibly similarly. Is anyone not with me on this? Does anyone have any questions so far? Okay. I realize I have my work from last time still up here. I didn't erase it. We're going to look at a sample question together involving this formula. This drawing is meant to be 2 electrons, which are spaced 1 millimeter apart. Although every time I look at it, I can't help but see a happy frog. So, we have 2 electrons, they're spaced 1 millimeter apart. What is the force between them? Before we do anything else, 2 electrons are both going to have negative charges. Are these 2 objects going to come together or be pushed apart? Pushed apart. Opposite charges attract, like charges repel. If 2 things have a negative charge, they should repulse from one another. If 2 things have opposite sign charge, they should move towards one another. Now, in order to find out what the actual force between these 2 particles specifically is, we need to first look at our formula for the electric force. I'm often going to write this as force electric in the notes to help differentiate it from other formulas with a force in them. So force electric equals KQQ over R squared. K is a freebie. We already know that. We need to know the charge of both objects present. We know these are both electrons, so we can look earlier in our notes and find what the charge of one electron is. So they both can have the same charge of negative 1.6 times 10 to the negative 19th coulombs. Last part is radius squared. We need to know how far apart they are. That is 1 millimeter. This drawing is not drawn to scale. These things are very close together. 1 millimeter converts to 0.001 meters. All this information, you can start plugging things into our formula. I do recommend you put this into your calculator yourself to make sure you can get the right answer. It is important you are only squaring the radius, and you should get an answer of 2.3 times 10 to the negative 22nd newtons. This is a very, very small amount of force, but the electrons themselves are very, very teeny tiny. They have incredibly small masses, so even though you would never notice a force this small, an electron would. When your mass is as small as an electron, a force this small will still make you take off in a rocket. But notice, we plugged in 2 negative charges and we got a positive answer. What would happen erase anything in your notes, but me asking you guys, what would happen if one of these was a proton instead?
What do you mean with neutron?
No.
Would the charge be neutral because they cancel each other out?
The total charge for both objects, if you added them together, like if both of them were contained within a specific space, and you asked what the net charge of that space was, you're right, the net charge would be 0. But if we're looking at the charge between both of them, sorry, the force between them both as separate objects, we would count them as separate objects for that. You were right that overall they would add up to 0. Like within my body, 1 electron next to 1 proton, that's happening all across every atom in my body, it'll add up to 0. And under very specific fusion reaction circumstances, 1 proton can fuse to an electron to make a neutron. So you were correct that that can happen, just not often. That's upper level chemistry. For the sake of just this formula, though, just looking at the forces between the two objects as separate entities, when they're both electrons, we plug in 2 negative numbers, those negatives cancel, and we get a positive answer. What happens if one of them was a proton instead? Now, protons have the same magnitude of charge as an electron. A proton's charge is positive 1.6 times 10 to the negative 19th, which means we would plug that number in instead. Now we only have 1 negative number in all of this. So how does our answer change if the two objects are of opposite charge? Negative. If the two charges involved here are of opposite sign, you're going to get a negative answer, because the only way for this negative to cancel is if you plug in a different negative. So if both of your charges are negative, you'll get a positive answer. If both of your charges are positive, you'll get a positive answer. But if one is positive and one is negative, you get a negative answer. And since they're of opposite charge, this tells us, we know from the colloquialism, opposite charges attract. This negative answer is what means they will attract to one another. If this formula gives you a negative answer, it means attract. If this formula gives you a positive answer, it means repel. That's worth putting in the sidebar of your notes. And while this and gravity are very similar, this is the key place where they're different. You can only ever have positive mass or no mass. You can't have negative mass, which is why gravity only points in one direction. It always tries to get things to move closer together. There is no gravity that repels. But because charges can be positive or negative, this formula can give you a force that goes in or out. That's the key way that these things are different. The key thing that distinguishes mass and charge from one another. Any issues with that specific example? Okay. This formula, this principle, is the reason why electricity happens. You can't have electricity. You cannot make electrons move from one place to another without some force acting on them to make them do it. Something has to push the electrons to make them move as electricity, and this is that force. The first form of electricity humans ever observed, that one would expect humans to have observed, is lightning. Barring maybe like observing static shock first, odds are the first electricity a human ever saw was lightning. And lightning is very much created by this force. So, this is a poorly drawn tree, and this is a poorly drawn cloud. Now, does lightning tend to happen much on a calm, clear day? No. On a big stormy day where lightning is prone to happen, there's usually lots and lots of clouds. In order for lightning to start, like the very beginning thing you need to sort of seed a lightning bolt into existence is a lot of clouds. And those clouds are going to drift through the sky and rub across one another, like when you rub your socks on the carpet. Clouds will develop a static charge from other clouds. One cloud will build up a lot of negative charge just from friction from other clouds. So the very beginning seed of a lightning bolt is one cloud developing a large negative charge. Now those electrons don't want to be anywhere near one another. Light charges repel, so those electrons want to get out. They don't want to be in the same cloud. As this cloud drifts along, it might eventually pass near a tree. Now, tall, pointy objects have a tendency to be positively charged due to the fact that they tend to dump most of their electrons into the earth. Electrons don't like to be near each other. They like to go into the ground so they can be farther apart on opposite ends of the planet. So tall, pointy things tend to be, as long as they're connected to the ground, tend to be positively charged. So this tree is likely the most positively charged thing in the area, and it's likely the tallest thing in the area. If we look at the formula, if the two charges are of opposite signs, and the bigger they are, the more force there will be, and the closer together two things are, the more force there will be. Since this tree is probably the tallest and most positive thing in the area, the electric force between the top of this tree and this cloud will eventually get so big that that force is strong enough to literally rip all these electrons through the air and into the tree. This force literally forces the electrons out of the sky and into the ground. And even though circuits and batteries aren't quite as dramatic, the same thing happens there. You create a situation where there's an electric force that forces electrons through your circuit, and they power your device. As electrons move through something, they do leave behind energy, which is how our appliances get powered by electricity. It's also why people tend to get burned when they get electrocuted, because if electricity is flowing through your body, it's leaving behind thermal energy as it passes through you, which is why trees get scorched, like they look scorched after they've been hit by lightning. Also why water tends to evaporate if you run electricity through it. But ultimately, this is the cause of all electric current. This is the source, this formula. Any questions so far? Well, I got this up here. Pro tip about how to not get electrocuted. First of all, don't be the tallest thing in the area. So if there's a big storm nearby, you want there to be tall things near you, but don't be like right under them. Be on the same city block, but don't be under them. 2, don't be the most positively charged thing in the area. You don't have a whole lot of control over that, but avoid charging yourself within reason. But then the last tip, if for some reason you know you're about to get struck by lightning, if you just know ahead of time for some reason I'm about to get zapped, then and only then, this is not step one. Step one is not raise your hand into the air. This is the last step if you know for some reason you're going to get shocked. You want to raise your right hand and stand only on your right foot. Any idea why?
As long as it's got your body.
If the lightning does go through your body, it's going to strike the part closest to it first, so it'll go into your hand. And it wants to get into the earth. It wants to go, like the electrons don't want to be near each other. They want to go into the ground so they can space out. Which means it's going to follow the most direct path from where it enters you into the ground. And as long as it enters your right hand and exits your right foot, it doesn't pass through your head, it doesn't pass through your heart. That's when it gets really dangerous.
Wouldn't that like give you bad bearings too?
Yes. All electricity can burn you, sometimes from the inside out. But it is survivable. There is one specific man who's been struck by literal lightning 7 times, and he's still alive. The article says he's a park ranger, so I assume it's a combination of an occupational hazard and also really bad luck. Maybe he has a very high iron diet, but it is survivable. When you get shocked, your muscles tend to seize up. Like it's like all your synapses and neurons are firing at once, and you just can't really control one muscle over another, so you just freeze. Which is really why you shouldn't shove a fork in a socket, because as soon as you start getting zapped, you will literally be unable to pull the fork from the socket. Your arm will lock up. Don't do it. Don't like a battery either. It is survivable, mostly if it's for a very short amount of time. And especially if you make sure it doesn't hit those 2 most important ones.